So we're still doing boson fluid. And let's first summarize what we have accomplished so far, what is the problem, and what is the solution that we found. Now, it could be a little bit cumbersome what we achieved yesterday. Some math, some approximations, mu goes to 0. So I want to summarize everything that we have done so far. Okay. So first of all, we have particles in a box. The volume of the box is V. The particles are not interacting with each other. They are free particles. The only thing that limits their behavior is the box. So this is the only constraint. The volume of the box is V, volume. Okay. And they're bosons, so they can occupy any energetic level that you like. We computed the average number of, or the total number of particles that we have inside a box. Remember, this number is conserved. So this is a trick that we perform for the grand canonical partition function and ensemble. When we unconstrain n, calculate the average n, and then say this average n is the exact number of particles that we have inside the system. Okay, so this is a controllable parameter for us. And we obtained that this parameter was G0 V lambda t to the third power, and the fully logarithmic function of the third 3 3/2 order of the fugacity. Okay. The problem with this, that the fugacity when mu goes to 0, okay, at least for very low temperatures, this is what we assumed. We know that the polylogarithmic function goes to 2.61, so it's a finite number. And this means that this n multiplied by lambda t to the third power divided by G0 V has to be smaller than 2.61. Now this is impossible. Why? Because we can control V and we can control N, and T is a specific temperature, so it can be happen because we can always increase N as we like. Okay. The solution is, well, we messed something somehow, and this mistake that we not on purpose have performed is that we cannot treat this, or we can treat the energetic spectrum in a continuum fashion. This result was obtained by the assumption that the energetic spectrum is continuum. It is continuum. The problem is that the number of particles at the ground state is extremely larger than the number of particles on the excited state. Okay? So usually when we assume that we can perform integration, we can turn summation into integration, what we assume that A, the parameter over which we integrate, in this case, was the energy, is continuum. Well, it's almost continuum in our case. Okay? It's very, very, very dense. We've seen that the maximal distance between two energies is 10 to the minus 14 Kelvin. It's extremely small. It's unachievable. Even now today, you can go to the lab of Lev Haykovich, where he cools atoms down. He's not even close to the 10 to the minus 14 Kelvin. Okay? So it's unachievable low temperature. So for us, the densities or the energies are extremely dense, and this is fine. The problem is, again, that the function over which we integrated has an extremely large peak at n0, and, well, normal numbers at n1 and n2 and n3. Okay? So we need to treat somehow properly the number of particles that are sitting at the ground state. Now, it's not just that the number of particles that are sitting at the ground state is huge, is that the particles that are sitting at the next level, so we calculated n211 divided by n111, is approximately 10 to the minus 7. Okay? So it's 7 orders of magnitude jump when you crosses from one epsilon, the energy, to the next one. And you cannot perform integration under such conditions. So what has to be done? You have to take properly the lowest energy separately and say, it is not part of my integration. It's a separate state. It's like a delta function behavior. So I take this as a discrete state and I take it separately from all the other integration that I perform. Okay? So we basically say that the number of particles is not this one. Okay? The number of particles, n, is n0 plus n excited. And what is n excited? N excited, okay, is this guy over here. Because when we perform integration, you can always omit a specific point. And we omitted one single point, the number of particles that are sitting at the ground state. Okay? So this calculation was okay for everything which is excited, because there are no huge jumps when you're treating the excited particles. There is one single jump, only one single jump when you treat what? When you treat the ground state level. So n excited, we are going to use this quantity over here. G0V lambda T 3 F3 halves of the fugacity. Now you can say, Stas, but you can again maybe use argument that there is a problem. There is a problem that the number of the excited, the particles of the excited states is smaller than 2.61, which is fine. Just fine. I only have a constraint on the total number of particles that are located inside the system. The number of particles, how they separated between the different states, well, I have no idea. This is the physics. I have to discover it. There are no constraints about how the different particles should be separated on different energetic levels. So the number of excited states indeed can be smaller than a specific number, which is fine. But the total number of particles is not. So I'm basically solving it as, yeah, there is a condition, but this condition applies only to the excited states. But the total number of particles, it's still a controllable parameter. And all the different other particles that I can push inside the system, all of them will go where? They will go to the ground state. And they all go to the ground state. So the physical picture is as follows. For fermions, if you look on the different energetic states, the fermions sit, due to the Pauli explosion principle, they all sit one on top of each other. Okay. They topple each other up. Okay. And then they feel all the different energetic levels up to extremely large temperature. Why? Because there is an Avogadro number of them in the bulk, and they have to sit or take energies one on top of each other. For bosons, it's not the case. For bosons, something completely different happens. So if this is the energetic spectrum, they all occupy the lowest, the ground state, basically. Now, we expect that to happen only for what? We expect that to happen for temperature goes to zero. Because indeed, for temperature goes to zero, everybody are sitting exactly at their ground state. There are no excitations. The excitations are permitted only because we have temperature. Okay? So at T goes to zero, everybody have to sit over here. But what we have found out, that this occurs, that huge macroscopic portion of the particles are sitting at one single level, even for finite temperature. Okay? T equals to Tc. Okay? where Tc, as we found yesterday, is exactly when this guy, or this guy F3 to F3 2 halves equals 2.61. So Tc is, write it down, was 2 pi h bar squared divided by m, 1 over 2.61, the average number of particles, G0V 2/3, 1 over k boson. Okay. And this is approximately, for helium-4, okay, is approximately 3 Kelvin. So it's a low temperature, yes, indeed, it's a low temperature, but it's not 0. Okay? And there is a huge difference between 3 Kelvin and 0 Kelvin. We should expect excitations, and we should expect that, well, there are some particles at the ground state, there are approximately very similar amount of particles at the next excited level, and then the next excited level, but no. What happens? We have huge portion of particles that are sitting exactly over here, a macroscopic portion, not just 10, huge number, and a very low number compared to the ground state sitting at the excited state, as we can see from here, 10 to the minus 7. Now, a question arises. How so? How could it be? You remember the differences between, if you look on the ground state, let's assume that the ground state is 0 energy. Okay. We can always shift all our energetic spectrum up and down, and let's assume that the ground state is epsilon. It's epsilon energy equals to 0. Okay. What is the excited state? We computed this yesterday. So it is epsilon 211. Epsilon 211 minus epsilon 111. Okay. This is the excited states. And this guy equals to 10 to the minus 14 Kelvin multiplied by K boson. Okay. So what we are saying is we are at temperature which is very low, around 3 kelvins. Okay? This is what I'm trying to tell you. The temperature is extremely low, it's around 3 kelvins. Okay? I'm saying that majority of the particles, big portion of all the particles are sitting over here at the ground state. You can say, well, yeah, sure, fine. But I expect that also a lot of particles we are going to sit at the next level. Why do I expect that? Because the energetic difference between those two levels is extremely small. So if you compare temperature-wise, so this difference divided by K bosons is 10 to the minus 14, extremely small. And the temperature where we observe this effect is 3 Kelvin. So the thermal fluctuations should cause excitations and should cause that huge number of particles that are sitting over here, okay, will be transmitted into the next level, and the next level, and the next level, and the next level. Why? Because temperature is much larger than the difference between the energetic levels, and it should smear up all the particles. But it's not happening. So this is the crucial point. We do expect, naively, that because of the differences between the different states are extremely small, and the temperature is not 0, and not to the 10 to the minus 14, but actually 3 Kelvin, 2 Kelvin, 1 Kelvin, okay, not 10 to the minus 14, we should have a smear of all the particles on different levels, but we don't see. Instead, we see that huge portion of the particles, when you be on the order of Tc, are still located at the ground state. Okay. How and why it's happening? So remember, what is N0? So N0, it is 1 over e to the power beta epsilon 1, 1, 1 minus mu minus 1. Let's call it what is N1. N1, it's 1 over e to the power beta epsilon 2, 1, 1 minus mu minus 1. This is the whole difference between the two states. The occupation numbers of the ground state and the excited state. Now, why we have a big portion of particles that are sitting here? Well, it occurs because we lower the temperature. So when we lower the temperature, T goes to 0, not until minus 14, but 3 Kelvin, 2 Kelvin, it's enough, as we see from there. Mu goes towards epsilon 111. Epsilon 111. Okay? It can approach from below only to the lowest energy. So what starts to happen? Of course, N0 gets bigger because this exponent over here approaches 1. So epsilon to the beta epsilon 111 minus mu minus 1, this goes to 0. And this causes to N0 to goes to infinity. But as mu approaches epsilon 111, and the number of particles are getting, at the lowest level, getting bigger and bigger and bigger, it actually protects the next level. Okay? So there is a huge accumulation of particles at the lowest level, but because mu can never cross epsilon 111, it cannot approach too much to epsilon 211, to the excited state, and this is why the lowest level is actually the boundary that protects from approach of the chemical potential towards the excited states. So mu never can approach really closely to epsilon 211. This is why we have such an effect. So there is an accumulation of particles on the lowest level and a huge jump in the occupation numbers between the ground state and the excited state. So it's all in the details where how far we can push mu. And the thing is, we cannot push mu that it could be larger than epsilon 11. The moment we cannot do this, this level is protected. And this is why we have huge number of particles at the ground state and much smaller number of particles at the next excited state and the next excited state, etc., etc. They are protected by the lowest level. So this effect, okay, it's called Bose-Einstein condensation. Why condensation? This state when all the particles sitting exactly in the same single state, well, it has a name, a condensate. And this is an explanation for a fantastic properties of matter. So we have superconductivity and superfluidity, which are the behavior of flow of matter. It can be for superfluidity, the flow of particles, and in superconductivity. Good morning. And in superconductivity, it's the flow of charges without friction. Okay? So whatever we describe here, it's not enough to actually understand why superconductivity and why superfluidity. Okay? But the explanation is there are systems like helium-4 or visco material. I'm sorry, that you can cool down, and when you cool it down, a condensate of particles is formed. In helium, those are the real atoms that are bosons, and they start to condensate on the lowest possible energetic level. And for superconducting materials, those are electrons that are forming. Electron is not a boson, right? It's a fermion. But there are pairs of electrons that are coupling together. They're creating a single boson, and they also form a condensate of pairs of electrons, which are called Cooper pairs, and they also form on the lowest energetic level. From here, to explain why there is no friction when everybody are sitting exactly the lowest level, you need quantum mechanics, and you need a single coherent states, and you need quantum entanglement. Okay, so but basically there is a one single wave function that describes all the particles in the system, okay, and the excitations actually are incapable of creating this or jumping those particles up. So what is friction? Friction is you lose energy. Okay? You go somewhere and you contribute your energy to somebody. They're all sitting at the same lowest level. They cannot contribute anything to anybody. Right? So what happens is they just flow, and since they cannot contribute any energy and they're all entangled together, there are no excitations, you don't have a loss of energy at all. You cannot lose it because if you're already at the ground state. This is why you have superconductors and you have superfluids. Basically, everybody are the lowest energetic state. They cannot lose anything, right? It's like somebody asking you for money, you can say, I have nothing. And they're all exactly at the same state. So this is a simple explanation. It's much more complex. You need quantum entanglement. But this is all due to what? To this Bose-Einstein condensation that happens at finite temperatures. There are superconductors that are superconducting at 180 kelvins, right? So superfluids are more complex. Fluids, you need to go to 3 Kelvin, 4 Kelvin, really, really low. But for superconductivity, you're getting something different at much higher temperatures of the order of 100 kelvins. Not room temperature, although there are claims today that there are superconductors at room temperatures. It's a lot of speculations around this issue nowadays. But for 100 kelvins, you do see superconductivity. This means that there should be something which is related to this Bose-Einstein condensation. Okay. So this is the explanation. But we need, in order to finalize this subject, we need to tell what is this N0, right? Well, you can say, well, this is N0, and we need to explain, to write what is the grand canonical partition function, grand canonical potential, and how and what are actually happening. So let's quantify a little bit the effects that we are now explained due to the condensation of particles. But let's see what we can observe, how this behaves, how to quantify this. So first, let's write down let's write down, where it is. It's here. Let's write down the grand canonical potential. Okay. The correct side. Okay. So first of all, the psi that we have written so far, psi equals to, if you remember, minus G0 divided by beta, integral from 0 to infinity, a log of 1 minus e to the power minus beta epsilon minus mu, the density of states d epsilon. So this is correct. This is correct for what? This is correct for all the excited states, right? We said the integration is fine, but we haven't included the ground state. So let's call it psi of excited. Okay. There also psi of 0. Okay? And we should find this out. What exactly this psi of 0? Okay? And this is only the psi, only the grand canonical potential for one single state. Okay? And you can say, well, why? How? What is a grand canonical potential for a single state? You need to macroscopic system, but this is not correct. We already seen this for canonical ensemble and also for grand canonical ensemble. The moment that our contributions to the energies are additive and factorizable, meaning that they are independent of each other, everything is additive. So the total grand canonical potential is just a sum over grand canonical potentials over all the different levels because they are independent. So we can write down this psi, total psi, as psi of all the excited states plus psi of 0. This we know how to compute, and this we'll see in a second how we compute it. So first of all, let's write down this function in a little bit more nicely than we have done before, and then compute psi of 0. Okay. So first I want to compute this psi excited. Psi excited is minus g0 divided by beta, an integration from 0 to infinity. Here we have log of, let's write it plus, and here we have 1 minus e to the power minus beta epsilon minus mu, and instead of the epsilon, what we have is v divided by 2 pi squared 2m divided by h bar squared 3/2 epsilon to 1/2 d epsilon. Now, I want to perform integration by parts. Okay? I want to perform integration by parts to get rid of this logarithmic function from here. Okay? Why, you will see in a second. So, g0 divided by beta. And when I perform an integration by parts, so let's get everything out. So v 2 pi squared 2m h bar squared 3/2 an integration from 0 to infinity, and here we have epsilon 1/2 log of 1 minus e to the power minus beta epsilon minus mu d epsilon. Now, integration by parts means, well, I keep the log and I take care of e to the 3/2. So I have 2/3. So we have g0 beta v divided by 2 pi squared 2m divided by h bar squared 3/2. Okay. And here I have, okay, so from this guy I have 2/3 epsilon to the 3/2 log of 1 minus e to the power minus beta epsilon minus mu in the limits of 0 and infinity. And from the other part I have minus an integral from 0 to infinity 2/3 epsilon to the 3/2. And here I have a derivative of the logarithm. The derivative of the logarithm is 1 over 1 minus e to the power minus beta epsilon minus mu. And in the denominator, I have minus e to the power minus beta epsilon minus mu. And the derivative is minus beta. And in total, I have the epsilon. Now, this guy, when epsilon is 0, so this term basically makes everything zeros out, the epsilon multiplied by log. When epsilon goes to infinity, so what we have is that 1 minus, when epsilon goes to infinity, exponent goes to 0, so we have a log of 1. And this term also zeroes out. So we don't have this term at all. So this zeroes out. And what we're left with is only this part over here. Which is, as excited, is minus. We have minus and minus. And beta cancels out. So we have minus g0 v divided by 2 pi squared 2m h bar squared 3/2. And here we have an integral, and we have 2/3. And here we have an integral from 0 to infinity of what? Of epsilon of 3/2. And let's make this denominator. We submit it into the denominator. So it is e to the power beta epsilon minus mu minus 1 d epsilon. Okay, you can say, Stas, you worked a little bit too hard. You made an integration by parts, but it's still, it's some sort of integral. But we have already seen this integral for what? For the computation of the total number of excited particles inside the system. So what we have seen, okay, is the following. We have seen that an excited is G0V by 2 pi squared 2m h bar squared 3/2, an integral from 0 to infinity of what? Of epsilon to the 1/2 divided by e to the power beta epsilon minus mu minus 1 d epsilon. So we have seen it like one lecture away. Now, we made an exact calculation of this integral, right? And we found out that n excited is G0 V divided by lambda t to the 3rd power of this function f3/2 of the fugacity. Now, you see the only difference, and the only thing that actually needed to be computed for the grand canonical potential is this integral. Okay. The only difference between this integral and that integral is that here it's epsilon to the power 1/2, and here it's epsilon to the power 3/2. The way to compute this integral is exactly similar to the way how we computed this integral. And if we do so, remember, we use Feynman trick, and we expand the denominator in powers, and then we obtain some Gaussian integrals, and we sum everything together. Okay? So when we do this, expansion of denominator to Feynman trick, free Gaussian integration, right? Exactly as we have done for the unexcited, we obtain a very nice result. What is the result that we obtain? I will write it down in a second. Just a second. Here it goes. Excited is minus G0 K boson T V divided by lambda T to the 3/3. And here we have, instead of 3/2, okay, so 3/2 is corresponding to the epsilon to the power 1/2. Here we are going, because we have another order of epsilon, so we have 3/2 over here, we're going to have f5/2 of the fugacity. So this is f excited. Right? So we know this. What is the grand canonical potential for the ground state? Well, it's actually even easier, because see, we have a connection between the number of excited particles and psi-excited particles. Why? Because it's had to satisfy the deep psi to d mu minus equals n. So we can do this only for the excited state, and we can do this also for the ground state. So minus d psi 0 d mu equals n0. What is n0? n0 is 1 over e to the power beta. Instead of epsilon, I have here 0 minus mu minus 1, which is 1 over the fugacity minus 1, which is the fugacity divided by 1 minus the fugacity. Because what is the ground state? Is epsilon 1, 1, 1, right? And I'm saying this epsilon 1, 1, 1 because I can always shift the energies up and down. I just say my ground state, I call it 0. It is fine. Okay? Remember, it's nothing to do what is the actual value of the ground state, but it all has to do that mu approaches the ground state. So I just shift all the energies ups and down, and it's always the same. Right? Remember, energy is always something that is defined up to a specific constant. So I define now my energetic spectrum. I just subtract from everything epsilon 1, 1, 1. And that's it.
You have to subtract from the chemical potential as well.
No. So yeah, so my chemical potential is now approaching what? It's not approaching epsilon 1, 1, 1, but it's approaching 0.
But you didn't do that for the other calculation.
I also did it. I did it. Where the integration started from? Why I haven't started here from epsilon 2, 1, 1 or epsilon 1, 1?
Something about, you said the chemical potential is negative, but the energies can be negative.
Then, so, right. No, the 0 is the starting point of my energetic spectrum. Right? Now, this is important. You can say the starting point of your energetic spectrum is epsilon 1, 1, 1. Right? This is correct. This is if we solve the Schrodinger equation and everything is fine. This is the ground state, the lowest possible level when nx equals 1, and y equals 1, and nz equals 1. Those are the lowest quantum numbers. And we have here epsilon 1, 1. I can call everything by saying, let's shift all my energetic spectrum by this lowest energy. Okay? Now, this means that everything is now in those coordinates, energetic coordinates, where 0 is epsilon 1, 1, 1. And now it's fine. Because the only thing that matters is that all the energies are higher than this epsilon 1, 1, 1. This mu, well, previously it could approach epsilon 1, 1, 1, and now it can approach 0. So everything is just shifted. Okay. This is important. So because I made a big deal about this epsilon 1, 1, 1. Because everything is so small, and we shift all our quantities, all the energetic spectrum and the chemical potential, everything, we shift this by epsilon 1, 1, 1, we're still fine. Remember, energetic spectrum is, you can always shift it by constant quantity. You learn it in the in high school when you learn mechanics and physics, that you can always, for your potential energy, decide what is my level, 0 height. The same goes over here. It's the same idea that energy is always defined up to a constant, and you can always define what this constant is. And we do this by defining that epsilon 1, 1, 1 is going towards 0. Okay, so now what we have that d psi 0 to d mu minus equals to what? Equals to e to the power beta mu divided by 1 minus e to the power beta mu. Right? So I can say, I solve this equation, and I can say that psi 0, it is k Boltzmann t log of 1 minus e to the power beta mu. Okay. Now, I have forgotten something. What I have forgotten? The degeneracy. So the degeneracy sits over here, this G0. Okay? This is G0. there is also degeneracy for the lowest level. Okay, so I don't know what is the degeneracy. I call it G0. So D0 is also sitting over here. So this is psi 0. Now, in total, and a huge mess in my papers, we have the following. That the ground canonical potential is psi 0 plus psi excited, which is G0K boson T log of 1 minus e to the power beta, without the minus, beta mu, or fugacity. Let's use fugacity for everything. 1 minus fugacity minus G0K boson T V divided by lambda T to the third power of F5 halves of the fugacity. I won't. This is grand canonical potential. Okay. We can use this to compute everything that we need. Okay. It treats separately the ground state and everything else. It's unusual to think about it. I have a continuous spectrum, but I still treat the lowest level separately. But we have to do this. The phenomena, the physical phenomena, forces us to treat the lowest level, although it's very close, indiscriminately close to the next excited level, but still something very special happens there, and we have to treat it separately. This is why we have this additional psi of 0. Okay, so let's compute some quantities, right? So we already understand this. We have a Bose condensation. Let's quantify. We have the grand canonical potential. We can use it, or we can use something else and calculate. For example, we know what is the number of particles in the excited state. Okay, we know this. But what is the number of particles at the lowest state, right? Previously, I just waved my hands and said, well, at the lowest state, there is approximately big number of particles. What is big? How big? What happens at the critical temperature? So they say the following thing. Okay. So we say the following thing. There is T above Tc, and there is T below Tc. For T above Tc, we say the following thing. The total number of particles, because nothing happens at the lowest level below critical temperature. There is, we get basically what we have said, that this, we have to treat this at low enough temperatures. So we say that at temperatures that are above this critical temperature, N is equals to N excited, which is this guy, G0V lambda T to the third power, F3 halves of the fugacity. What is it? What is then N0? N0 is N minus N excited particles at the excited states, and this is simply 0. Okay, because it's asked, how can it be 0? Oh, it's almost 0, right? Think about it. I have an infinite number of states. Each state is contributing something. Well, it's not exactly 0, but it's a very small number compared to the excited states. Okay? So the truth to be written is that N divided by N total goes to 0. Okay? So there could be some particles at the 0 level. It's like the same, that because I have a continuous spectrum, so I have a density of states, but each state actually contributing 0. It's the density that contributes something. So I don't have almost any mass at each specific level because I have many of levels. So there are no particles at the ground state, or almost no particles at the ground state. what happens at Tc?
You have to think it probabilistically, right?
Exactly. I have to think it like a mass. Okay, so if I have a string, okay, and I have mass in some specific portion of a string, but what is the mass of a very specific point? 0. Okay, so the thing is the same over here. I have particles at a spectrum of states, but what is the number of particles at each specific state? It has to be 0 because the spectrum is continuous. Okay? And it's the same goes with probability, right? So what is the probability to hit a given point on this board? It's 0, right? It is 0. But what is the probability of hitting a specific area? Well, it's the area divided by the total area of the board. Okay? So this is the idea, the same idea. I'm not treating this 0 ground state differently when my temperature is high enough, because it's part of the spectrum. When the temperature is low enough, you have to take care of this guy over here. Great, so what happens at T lower than Tc? Let's do the same trick. Let's calculate the n excited, and then from n to n excited, we can calculate the n0. Now, so what is n excited at T lower than Tc? This computation was fine for any temperature. Now, what happens when the temperatures are getting to Tc? So exactly at Tc, this F3 of 2/2 converges to a given number, 2.61. Let's call it F3 halves of 1. So we know that n excited is G0 V. We still have lambda T of 3 half to the power of 3. And here we have F3 halves of 1. So the difference is, the only difference is the behavior of this polylogarithmic function. For T larger than Tc, it's something, because it's just a fugacity, is exponent of beta mu. I don't know what's exactly mu, but it is what it is. And I know that FTC it converges to this number, and I'm only going to use this number. Lambda T stays still lambda T. Okay. What is n excited at Tc? N excited at Tc is exactly G0V, lambda T C to the third power. It's still F3 halves of 1. And it equals to the total number of particles. Why? Because I assume that this condensation, when it starts when this function starts to get me problems, when it cannot grow anymore. But exactly at that point, this crossover point from normal state to a condensate occurs when T equals to Tc. But exactly at Tc, the total number of particles is still provided by the total number of particles in the excited states. So I can compute the total number of particles by using this function over here. Okay.
The first one is the fugacity, right?
Yes. 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 So let's compute n0 divided by n. So n0 divided by n is simply n minus n excited divided by n. What happens over here? So n0 divided by n is 1 minus n excited divided by n. It's 1 minus. So now we can submit all of those guys. So we have n excited, and we have n, which is n excited at Tc. So we have G0V divided by lambda t to the 3 of 3 halves of 1 divided by g0v of lambda tc, okay, to the third power of 3 halves divided by 1. We obtain that n0 divided by n equals 1 minus lambda tc to the third power divided by lambda t. Now we submitted this thermal wavelength, and the only thing that differs for lambda tc and lambda t is the temperature dependence. This is 1 minus t divided by tc 3 halves. So a very neat and nice result, okay, for the behavior of how many particles are sitting at the excited state. You see what we obtain. This is temperature. This is n0 divided by n. For t larger than Tc, it's basically 0. Why? Because this is just a single state, there is no condensate, and the total number of particles, or the portion of the number of particles of a big part of an Avogadro number of particles is basically 0. But as we cross the temperature, this condensate starts to appear. This is what we're getting at. This is a very neat transition from 0 and what is we indeed expect in for a continuum spectrum of particles, and something completely unexpected that appears not for 0 temperature, but actually for final temperature. Right? And the order here is 3 to the halves. We won't study Ginzburg-Landau theory or critical exponents this year, but this is a critical exponent of the system. Great. What happens?
This is a second order expectation, right?
Yeah, in some sense. So it's not a first order. There is no jump, right? It's a continuum transition. Okay, the number of particles was 0, and it's not jumping to something. It's a continuum transition from 0 to something else. It's not exactly second order. And the phase transitions are defined by some interactions. We don't have interaction over here. Okay, so think about it. We obtain it only because of the properties of this mu. There are no interactions between particles. Phase transition is an outcome of interactions. Here it's something else. It's an interaction of all the particles with a single 0 state. So it's a little bit different than a regular phase transition. Okay, so this is very nice, but what they measured in experiment, right? So I'm saying to you, yeah, I have number of particles at 0 state, and it's not 0, it's actually something, and this something is described by t divided by tc. What people have measured in experiment? I told you about helium-4, okay? This is a superfluid material that actually people observed it flow without friction. Okay, it can flow upwards, it can flow downwards, it can flow in a circle, and there is no friction for helium-4. People observe superconductivity. What they observe, what they actually observe, they cannot go and measure the number of particles at the lowest state. It's a quantum information, a microscopic information. You cannot measure this. What you can measure? Okay. What you can measure is, as always, with at least this part of statistical physics, is energy, and specifically specific heat. Okay, so let's see what happens, what exactly been measured. I'm telling you about all this theory, but people first measured something, and then they started to try and understand what exactly is going on here. They haven't measured this. They measured something else, which is energy and specific heat. So let's calculate the specific heat to see how exactly it looks like. Because maybe one day you will become an experimentalist, and you need to understand what exactly do you see. Nobody is going to measure the number of particles at the ground state. Well, not in statistical physics. Okay, so what we want to calculate is calculation of specific heat and calculation of energy. Okay, so specific heat is easy. CV is du to dt. So the moment that we have u, we need to compute its derivative. How we compute energy? So the average energy is the same story as always, right? So either we start with the derivative of our grand canonical potential with respect to something, okay? Or we calculate it from scratch using the probabilities, right? So if we focus on energetic level epsilon, okay, so what we have for energetic epsilon, level epsilon, it is U of epsilon, the average energy, it equals to a sum, and epsilon goes from 0 to infinity, of epsilon and epsilon. So the number of n is the number of particles that are sitting at level with energy epsilon, multiplied by e to the power minus beta n epsilon minus n epsilon mu divided by z epsilon. So this is the value of the energy if n epsilon particles are present, and this is the probability that this level is occupied exactly by n epsilon particles. Okay? Very easy. It's always the same probabilistic structure. Next thing to do is to recognize, well, this is a derivative. Again, this final trick, it's always the same. This is a derivative with respect to beta of this guy. Not exactly with respect to beta, because you see when we take derivative of this guy with respect to beta, we should get downwards not only an epsilon, but also an epsilon mu. Okay? So what we do, we say the following. So u epsilon equals, let's take z epsilon out. We have z 1 over z epsilon. And inside here, we can say, let's take a derivative with respect to beta, but we keep everything which is beta multiplied by mu constant. So we have n epsilon 0 to infinity minus d to d beta of e to the power minus beta and epsilon minus mu, but we keep this beta mu constant. Okay. When we do this, we can perform the Feynman trick. Why? Because we take a derivative with b beta, but everywhere where there is beta multiplied by mu is a constant, it's not a derivative. Okay, okay, now again, what is this? It's 1 over z epsilon, and we have d to d beta of what? A summation n epsilon goes from 0 to infinity of e to the power minus beta n epsilon minus mu, while we keeping beta mu constant. Okay. What is this? This is just a partition function. Okay. Because this is this as of definition of partition function, the summation of all those exponents is simply zeta epsilon. So it is 1 over z epsilon d to d beta of z epsilon keeping beta mu constant. And we can take this z epsilon inside, and we have 1 minus d to d beta of log of z epsilon, okay, where we're keeping beta mu constant. Very nice, okay? Why it's very nice? Because u, it's a summation of epsilon, of u epsilon. We go over all the different energies of the spectrum and we compute the average energies for each state, energetic state, and we sum up all the different energies. Why? Because the average of a sum is a sum over averages. This is the crucial part that you have to memorize from probability theory. This is always holds, which means that we have minus d to d beta of a sum over epsilon, z of epsilon, while keeping beta mu constant. Log. Okay. But remember, what is sum over epsilon over log of z epsilon? What is this? Well, if it's 1 over beta minus, it is just the grand canonical potential. Okay? So we reach the following form. U equals to d to d beta of beta grand canonical potential while keeping beta mu constant. Okay. It's a very nice formula. Now, you can then ask, Stas, this is great, this is fantastic. What kind of psi you're going to use here? What is the psi? Well, you can say, well, above Tc, this is the psi of the excited states, because there is nothing peculiar going on above the critical temperature. So you have to use for psi on the excited psi, the psi of the excited states, as we computed it from the integration, etc. But below Tc, well, below Tc, you probably have to use what? Probably have to use the, not the excited psi, but you probably use also this contribution from the zero state, right? Wrong, you don't really need to do this. And why is it so? What is the average energy at the ground state? 0. So it's not part of the contribution to the sum. So we do not neglected it when we translated this summation into integration. It's simply not there, right? So because the average energy, there is no contribution from the ground state to the average energy. You don't need it. Why? Because we started our energetic spectrum from 0. So the average energy of all the particles that are sitting inside this energetic level is by definition 0. So there are no problems when you compute the average energy.
And the only contribution in the grand canonical potential, it was from the fugacity, and we're keeping the fugacity.
Fugacity constant, exactly. So this is the mathematical reason why it still applies. You're keeping beta mu constant, you take a derivative with respect to beta, and it's simply 0 of the psi 0. But it's why it's not contributing to anything, this specific state, because it's not there. It's not there from first principles. Okay, so what was our so our psi was minus G0 of K boson T, V divided by lambda T to the third power, F 5 over 2 of the fugacity. Now this means that U, and I'm not going to take this derivative, it's actually already simple. This means that U equals to 3/2 K Boltzmann T G0 V divided by lambda T to the third power F 5/2 of the fugacity. So we have this number right now. Therefore, we can calculate something. We have U. First of all, let's see how U behaves above TC and below TC. U, T larger than TC, and T smaller than TC. And say, well, why should be there a separation for above TC, below TC? Because of this guy. Above TC is just F, this polylogarithmic function of fugacity. It's a regular function, nothing funky going on there. Below TC, we just put here 1. Because this function at TC converges to 1, we have to put 1 over here. Okay, so let's try and see how it's actually working out. So first of all, we have the following. Remember that for both of this, unexcited equals to G0V divided by lambda T to the third power F 3/2 of the fugacity. And I want to write down, because I know that something is going on with the excited states, and I want to use their properties in order to describe the U properties. Okay, so see that this is very, very similar. So I have G0 and I have V and I have lambda T and I have 3 at the form of the energy. And also here for what? For the excited states. So I can write down that the unexcited divided by F 3/2 of the fugacity equals to G0V lambda T to the third power. Okay. So we have U equals to 3/2 K Boltzmann T multiplied by unexcited, okay, B instead of this guy, and I have a prefactor F 5/2 of the fugacity divided by F 3/2 of the fugacity. Now, if you look on this formula properly, you will recognize something very interesting. If I forget about this part, what do I obtain? I have 3/2 K Boltzmann T multiplied by the number of particles. So, sorry?
The ideal gas.
The ideal gas. Exactly the ideal gas. Oh, I have 3-dimensional problem. Each dimension, so there are no interactions. Okay? There is only kinetic energy. Kinetic energy is K Boltzmann T. So I have here only kinetic energy, right? All the parts. So what is 3/2 K Boltzmann T is the energy, kinetic energy of one single free particle multiplied by the number of particles that I have inside the system. Which is great. This is what I expect for regular particles. But those are bosons and they have this condensation. So something mixed up. And I have quantum properties, etc., etc. So I have this prefactor. Okay. So everything that we have talked about, okay, is basically sitting in this prefactor, this polylogarithmic functions and the ratio of those two. They describe everything. Okay. So let's finish this computation. And I want to use this formula because I know how unexcited behaves above TC and below TC. And I know how this polylogarithmic function behaves when I'm above TC and below TC. So it's almost an ideal gas. We started with the gas, but it's almost an ideal gas because of the quantum properties of bosonization and etc. We have an additional prefactor. I think it's a beautiful formula because it's like, yeah, I expect this, well, something that I do not expect, but I can quantify everything by this ratio over here. So first of all, let's do T larger than Tc. So T larger than Tc is just this formula. U equals 3/2 K Boltzmann T and epsilon and excited F 5/2 of the fugacity divided by F 3/2 of the fugacity. Let's see if it's fine for extremely large temperatures. So when temperature T goes to infinity, what happens over there? Now, I don't care bosons, fermions, I don't care about anything when my temperature is high enough, and because there is no interactions, I expect U equals to 3/2 K Boltzmann, the number of particles. Okay, so let's see if we indeed obtain this. Now, I remind you, what is F alpha? F alpha of X, it is a sum I goes from 1 to infinity, I'm sorry, of X to the power I 1 over I to what? To the power alpha. Okay, so T goes to infinity. Beta equals 1 over K Boltzmann T goes towards 0. Fugacity, it's e to the power beta mu, goes towards what? 1. Right, this is okay. Towards 1. Yes. Fugacity goes towards 1. Okay. So what starts to happen over here? So I have when X is exactly 1. Okay. Now fugacity is not going towards 1. Beta mu. Something strange is going on here. Right. Because when mu goes to 0, I expect that fugacity to go towards 1. Okay, but I expect that when T goes to infinity, beta goes to 1 over K Boltzmann T, and it goes to 0, right? That fugacity is indeed 1. This is strange. This is strange. Takes to I 1 over fugacity. Because, okay, I will tell you what I want to discover and we'll discuss it maybe later. So what I want to say is the following, is when I have F alpha of X and I have F beta of X, and I know when X goes towards 0, okay, I need only to take the first powers of this. So this is X to the first power multiplied by 1 over 1 to the power alpha divided by X to the first power multiplied by 1 over 1 to the power beta And this goes to x divided by x, and it equals 1. So, and I don't understand how it's related to the fugacity, I will find out later, but when t goes to infinity, the claim is that the polylogarithmic functions, the ratio for t goes to infinity, the ratio of f3 halves, f5 halves of the fugacity divided by f3 halves of the fugacity, it goes to 1. Oh, I know where it's coming from. I know where it's coming from. I will explain it. I want to finalize. So it's actually coming from also from the n-excited. It's coming also from the n-excited. I will explain it a little bit later. But what happens at t goes to infinity? U goes to 3 halves k boson t n. And this n can be calculated exactly at the Tc. I will define everything in a bit. So this is for t larger than Tc. What happens for t smaller than Tc? So for t smaller than Tc, I have the following thing. So U equals to 3 halves k Boltzmann t n excited, and instead of fugacity, I'm simply putting 1 over here. So this is the thing, it's not just the behavior of the ratio for t larger than Tc, it's also the behavior of n excited. I will define it in a second. So I have here n excited f5 halves of 1 divided by f3 halves of 1. Okay. Now, we know that n excited is not equal to the total number of particles. So we plotted this way. 3 halves k Boltzmann t, the total number of particles, not just the excited, but the total number of particles. Okay. And here we have n excited divided by n, f5 halves of 1, f3 halves of 1. Now, we calculate this guy. N excited by n is t to the Tc, right? So we have 3 halves k Boltzmann t. We have this ratio, and this ratio is 0.51. Right? It's not 1/2, but 0.5123 something. We have multiplied by the total number of particles multiplied by 0.51 multiplied by this Ne divided by n, but we calculated this already, and it is T divided by Tc to 3 halves. All right, so we obtain that for T divided by Tc, it is 3 halves k Boltzmann T n T divided by Tc multiplied by 0.51.
It's 3 half, right?
It's 3 halves.
In the power.
So let's look on the energy as a function of temperature. And we have a Tc over here. So for low temperatures, it is growing with this T and the T to the 3/2. So it's going like this. And above Tc, it's doing something like this. Let me plot it properly over here. So U is 0.76 nk Boltzmann T, T divided by Tc to the 3/2. This function slowly approaching this behavior. So this is U from here, and the high temperature limit is U equals to 3/2 n k Boltzmann T. So instead of just computing this in the T to infinity limit, we have also to compute the unexcited property. This is how we obtain this 3/2 n k Boltzmann T. We're almost out of time, so the last thing that I want to compute today is even not to compute, just to show you, is what is CV. CV is du to dt. So we have to treat properly U above the critical temperature and U below the critical temperature. Okay, so U below critical temperature is just this guy, and U above critical temperature is this guy. Okay, so we have U, it is 0.76 nk Boltzmann T, T divided by Tc of 3/2, T below Tc, and we have 3/2 k Boltzmann T and E, F 5/2 of fugacity divided by F 3/2 of the fugacity, okay, at T above Tc. And we know that when n excited multiplied by this prefactor, right, it has to converge to the total number of particles in the large temperature limit. Okay, so when you take derivative out of this guy, you obtain a spectacular behavior. This peak, not a little peak, occurs at the critical temperature. Okay. And to what value the CV converges for large temperature? You should know this.
K Boltzmann
Exactly. K Boltzmann what?
times 3n.
It's exactly. So 3/2 K Boltzmann multiplied in the number of particles that we have inside the system. Okay. Now, this type of behavior have a name, because this looks like a lambda, a Greek letter lambda, right? So this is lambda, right? It looks like a lambda, and therefore the name lambda transition. So this lambda transition, this peak in the specific heat was observed experimentally, and this has started all this interesting incursion inside the statistical physics. So it's not that, oh, we start from boson gas and then we obtain such and such behavior. It's the other way around, as almost always. We see some new facts, fantastic, great facts in experiment, and then we start to understand how nature is working. Okay, so what is the model? What is the explanation behind all this? So although we started with the boson and free gas and etc., people started from this, and then we worked our way into the physics and understanding how physics works the other way around. So, but you can actually see such plots appearing on experimental papers. Okay. This is the lambda transition. It occurs due to the bosonization, condensation of bosons. We are done. So the plots to remember: CV, U, and plot the third plot, which is temperature and N0 divided by N, although people do not compute it in experiments. So this is DC. This plot. And the thing that usually brings us to the next subject in the class are phase transitions, although we treated phase transition from thermodynamical properties, but here we also have it's not a jump, but something peculiar happens in those points. Okay, over here, over there. We've seen that when something peculiar happens for energies or other quantities, the matter changes its state, and we know that here the matter changes its state. So what we are going to do next, although we have only one single lecture left, but usually what is done in the regular semester, we explore critical transitions, okay? Phase transitions, but not from the perspective of thermodynamics, but actually from the perspective of statistical physics and ensembles and etc. How we treat those points and what exactly happens there. Not we just say, well, let's write the free energy somehow of the van der Waals gas. No, when we start from the microscopical state and we use canonical ensemble or grand canonical ensemble, what actually happens over there? Okay? We will maybe try to solve the transition from paramagnet to ferromagnet and the simplest case of Ising model. Let's see. So we are meeting next Tuesday, and that's it for today. Thank you.
אפשר שאלה?
Sure. Shoot.
לא יודע אם פספסתי את זה, אבל למה בעצם פה אנחנו יכולים להגיד את זה בטמפרטורות גדולות? סליחה, טמפרטורות מעל T קריטי.
קודם כל אפשר לחשב את זה בדיוק, אוקיי? והטענה היא כזאת, מה קורה, זה טענה קצת פיזיקלית, יש פה טיפה לפנות אליהם, קצת.
זה לא T שואף
לא,
זה לא T גדול מאוד מאוד, זה פשוט T מעל T קריטי.
הטענה היא כזאת, קודם כל אפשר לחשב, זה לא בדיוק נכון, אוקיי? אבל זה עובד ככה, בואו נחשב את זה במדויק.
הגרף לא באמת נראה ככה.
נכון. מה זה N0? אוקיי, N0, אנחנו יודעים שזה capacity, E בטא מיו, אוקיי, E בטא מיו, מינוס 1 פחות 1. 1 פחות. עכשיו מיו הוא לא בדיוק 0, ובטא הוא לא 0, אז איזשהו מספר. אוקיי? זה איזשהו מספר, נקרא לו x. אוקיי? המספר הזה הוא מספר סופי. הטענה היא כזאת, אני לוקח את n0 ומחלק אותו ב-n. אז יש לי x שהוא מספר סופי שהוא תלוי רק בטמפרטורה, בפוגסיטי, אוקיי? גדלים שהם לא תלויים בכלל בכמות החלקיקים שיש לנו פה, וזהו, אז יש לי x חלקי n. כמות החלקיקים שיש לי היא כמות מקרוסקופית, סדר גודל של אבוגדרו, x חלקי 10 בחזקת 23. אני טוען שה-x הזה הוא לא קטן, הוא לא גדול, הוא לא יכול להיות מהסדר גודל של 10 בחזקת 23 בגבול המקרוסקופי, אוקיי? ולכן אני טוען שהגודל הזה פחות או יותר 0.
אבל למה...
לא בדיוק, אבל פחות או יותר 0.
כן, אבל ראינו שבטמפרטורות נמוכות יש הרבה חלקיקים של כן.
נכון.
שאין אפס די גדול. למה פה אנחנו מניחים שאין אפס הוא לא כזה גדול?
אוקיי. אני טוען שבתיק קריטי, בדיוק בתיק קריטי, ההצטברות מתחילה להיווצר. אוקיי? כלומר, משהו מתרחש בתיק קריטי, הפונקציה הפולילוגריתמית לא יכולה כבר לתפקד, אוקיי? ואני מתחיל, סליחה, ואני מתחיל להסתכל על כל על היווצרות של חלקיקים. אבל בדיוק בטמפרטורה, כי תשים לב, אנחנו צריכים לעשות איזושהי השוואה, כמו, לכן זה דומה למעבר פאזה. אנחנו מסתכלים על גודל של חלקיקים, ואנחנו טוענים כזה דבר. הרי הדבר הזה עובד איפשהו. בטמפרטורה מסוימת, הנוסחה שפיתחנו היא מפסיקה לעבוד. וצריך להתבצע, אנחנו צריכים לעבור בצורה רציפה מכמות חלקיקים שהייתה בטמפרטורה כשהכל מתנהל כמו שצריך, לבין מתישהו שהתופעה מתחילה להיווצר. היא לא באה יש מאין, היא פתאום באה מכך שהמצב הזה הוא הופך להיות הרבה יותר מועדף, ואז מתחילה זליגה של חלקיקים אליו. הטענה היא שזה מתבצע בדיוק בטמפרטורה קריטית, כלומר, מעבר לטמפרטורה הקריטית, יש לי איזשהו מספר סופי של חלקיקים, אוקיי? חלקי מספר עצום של חלקיקים, לכן היחס הזה הוא כמעט אפסי. מצד שני, בטמפרטורות מספיק נמוכות, אוקיי? אנחנו כבר צריכים לקבל משהו שהוא לא אפסי, ואז הטענה שלנו צריכה להתחיל לעבוד. כלומר, אם אני מנסה להבין אותך, אתה אומר, סטאס, אתה מצד אחד, אתה פעם אמרת לי שאין אפס הוא גדול, נכון? ועכשיו אתה אומר לי, אין אפס הוא קטן. מה בדיוק מתרחש פה? אז מה בדיוק מתרחש פה הוא בגרף הזה. ככה וככה. Okay. ההתרחשות בדיוק נובעת מהגרף הזה. כשאתה יורד מספיק בטמפרטורות, ה-N0 באמת מסדר גודל שלהם. כשאתה עולה מספיק בטמפרטורות, ה-N0 חייב להיות זניח. כי החלקיקים מתחילים להתפרס על כל המרחב שלך, על כל הספקטרום של הטמפרטורות שלך. איפשהו פה באמצע?
זה הקריטי.
זה הקריטי.
אוקיי.
למה בדיוק חייב להיות התקריטי הזה? אוקיי? למה בדיוק חייב התקריטי הזה? בגלל ההתנהגות של ה-F. יש הסבר הרבה יותר טוב כשמשתמשים בקוונטים בקוונטיזציה שנייה. הסבר הרבה יותר טוב. זה הסבר משהו שנקרא, אנחנו לא נלמד את זה כל כך, אבל וינפילד. אבל ההסבר הקוונטי הוא משמעותית יותר טוב, רק שאני לא רציתי להכניס לכם פה. אי אפשר להכניס לכם פה קוונטיזציה שנייה.
מה זה קוונטיזציה שנייה?
תלמד את זה בקוונטי מתקדם. כשאתה מתאר, יש לך קוונטיזציה, עזוב, ארוך.
אי אפשר על רגל אחת.
לא על רגל אחת. אבל תכלס מה שאני ניסיתי להסביר, ולכן יש פה לא מעט נפנופי ידיים. שים לב, זה ששמת לב, זו באמת נקודה בעייתית פה. אני מצד אחד אומר את זה, מצד שני אני אומר את זה, אבל זה קונסיסטנטי כי יש מעבר. אוקיי? כי יש מעבר מכאן לפה. אוקיי? ומעבר מתרחש בטמפרטורה סופית, והטענה שלנו שהטמפרטורה הסופית היא מגיעה מכך תשים לב, יש לנו איזשהו גודל, ה-n-excited הזה, שהוא g0v חלקי למדה t, חלקי כפול f, שלושה חצאים של e בטא mu. הגודל הזה הוא מצביע על איזושהי טמפרטורה קריטית מיוחדת. כי בוא נעשה את זה ככה. תשים לב. אז יש לנו, בואו נרשום פנימה את כל הלמדות שלי. אני אף פעם לא זוכר את הטרמל ווייב לאנט הזה, אז נוציא אותו מהווידם. בואו נרשום את זה עם כל הטמפרטורות, עם הכל שיש לנו פה. אז יש לנו n excited שווה ל-G0, מספר, אפשר לשכוח ממנו, זה 1, 2, זה ה-degeneracy. הווליום שלך חלקי. למדה T, פה זה בשלישית. אז 1 חלקי, אז יש לנו פה חזקה של 2m k בולצמן T חלקי פעמיים h בר פאי, ופה יש f 3 חצאים של e בחזקת בטא מיו. אתה מתחיל להקטין את הטמפרטורה שלך. אז n אפסילון חלקי ווליום. הגודל הזה, בואו נקווה אותו. הוא גודל קבוע. אוקיי? פה יש 3 חצאים. בואו נוציא את כל הדברים הקבועים האחרים שיש כאן. אז יש לך פה 2h בריבוע פאי חלקי m k בולצמן, או נשאיר את זה k בולצמן t, פה, זה שווה בחזקת 3 חצאים, שווה ל-k בולצמן t בחזקת 3 חצאים, f 3 חצאים, e בטא מיו. הגודל הזה אתה משאיר קבוע, למה? הווליום שלך קבוע, מספר החלקיקים שלך, נניח אתה לא נותן להם לברוח באמת, אז המספר החלקיקים שלך גם קבוע.
אז מספר החלקיקים ברמה מסוימת של אנרגיה, אני לא יכול...
כל, זה כרגע, נניח כשהתייחסנו לזה פה, זה בכל, זה לא n אפסילון, זה n excited, אבל ככה אנחנו חישבנו את זה. זה כל החלקיקים שלך, נניח שזה כל החלקיקים שלך, אוקיי? אתה גם מקבע את זה ולא נותן לאף אחד לברוח, אוקיי? גודל זה כל מיני קבועים אלמנטריים, זה גם קבוע. אתה מתחיל להקטין את T הולך ל-0. אוקיי? אתה מקטין את T. כשאתה מקטין את T הולך ל-0, משהו כדי לאזן, כדי שהצד שמאל נשאר קבוע, כדי לאזן את הגודל הזה שהולך ל-0, הגודל הזה צריך לגדול. נכון? אז T הולך ל-0, אז הגודל הזה הולך לאיכשהו אינסוף, ככה שהם מאזנים אחד את השני. נכון? אתה יכול לעשות את הטמפרטורה שלך קטנה כמה שאתה רק רוצה. אין שום בעיה, ברמה עקרונית. את זה אתה לא יכול. כי ה-F 3 חצאים
מתכנס ל...
הוא אומנם גדל, והשיפוע שלו פה אינסופי, אבל הוא מתכנס לגודל סופי. אחר כך הוא מתבדר, אבל זה כבר משהו שאומר שמשהו דפוק קרה אצלך. אז הוא מתכנס לאיזשהו גודל. אוקיי? כלומר, אתה מגיע לאיזושהי טמפרטורה קריטית, שאם אתה תלך מתחת אליה, הגודל הזה הוא כבר לא יזוז. כי האקספוננט הזה הוא גג יכול להיות 1, האפסילון, במינימום הוא יכול להיות 1, ו-F 3 חצאים לא יזוז מהערך הזה של 2.61. אז יש לך גודל קבוע, יש לך גודל שהולך ל-0, יש לך גודל שאמור לאזן אותו, והוא לא מצליח לאזן אותו כשאתה עובר איזושהי טמפרטורה מסוימת, כי הוא לא יכול לגדול יותר. זה יכול לקטון כמה שאתה רק רוצה, זה יכול לגדול כמה שאתה רק לא יכול לגדול מעבר ל-2.61. זה אומר שיש לך איזושהי נקודה בעייתית פה, והנקודה הבעייתית זה הטמפרטורה הקריטית. שמעבר לטמפרטורה הקריטית, הנוסחה הזאת כבר לא נכונה. וזהו, ומשם אנחנו ממשיכים הלאה. וכל הסיפורים האלה על N0 גדול ו-N0 קטן, זאת אומרת בסדר, ברגע שיש לי טמפרטורה קריטית, בוא נלך אם אני אלך מספיק קרוב ל-0, אז בוודאי ש-N0 יהיה מאוד 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 גדול. רק שהטענה היא, כש-N0 גדול גם N1 גדול, וזה לא נכון. זה לא מה שקורה. אבל עצם זה שיש לך טמפרטורה קריטית, אתה רואה מהטענה הזאת. גודל שיכול ללכת ל-0, גודל שמוגבל, וגודל של קבוע. זה לא יכול להתקיים. באיזשהו שלב הנוסחה הזאת יוצאת מאיזון, ואנחנו קוראים לנקודה, הטמפרטורה שבה הדבר הזה יוצא מאיזון, כטמפרטורה קריטית שלנו.
אבל למה אנחנו בכלל מניחים שעד הטמפרטורה הקריטית זה עובד? למה מלכתחילה
עובד, עשינו חישוב, יש משהו רע, שום דבר לא מתנהג רע. שום דבר לא באמת מתנהג רע.
אבל בסוף הצלחנו למצוא ביטוי יותר מדויק
יפה מאוד, אבל תיקח אותו בחשבון ותראה שהוא לא תורם יותר מדי כשהטמפרטורות שלך גדולות. פשוט לא תורם.
אוקיי, אז אפשר פשוט לרשום את הביטוי של n שווה n0 ועוד n excited.
כן, אתה תראה שהוא לא תורם יותר.
לקחת את הטמפרטורה ל-T קריטי ואנחנו רואים שאנחנו נשארים פחות או יותר רק עם n excited.
כן. 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 אתה תראה את זה.
הבנתי.
אתה תראה את זה. כן. באמצע הייתי צריך לנפנף בידיים. הייתי חייב לנפנף בידיים כדי להסביר לך מה בדיוק מתרחש. אני צריך את זה, ועכשיו אני גם צריך לך באיזשהו שלב את זה.
כן.
למה? כי יש פה נקודה עדינה. תשים לב, גם יש פה משהו... הקיבול חום פה הוא יורד, אנחנו אף פעם לא ראינו קיבולי חום יורדים. זה כבר מצביע על משהו מאוד, מאוד בעייתי שמתרחש. הירידה הזאת פה של הקיבול חום. זה מה שהם שמו לב. הם שמו לב שהקיבול חום, כלומר הם מודדו את זה בטמפרטורות גבוהות, התחילו להקטין את הטמפרטורה, והקיבול חום מתחיל לעלות. שזה, וואו. בדרך כלל קיבול חום שלך יורד. תמיד אם אתה תגזור את זה, אוקיי, קיבול חום שלך הוא תמיד ככה.
כי אנרגיה אמורה לעלות עם
כן,
טמפרטורה.
בדיוק.
בדיוק. דבר ראשון.
נכון. האנרגיה גדלה עם טמפרטורה, ופה אתה מקבל שהנגזרת של האנרגיה לפי טמפרטורה יורדת. זה לא, הוא חיובי. אז הנגזרת שלך חיובית, היא תמיד חיובית, אבל היא עולה יותר לאט מאשר לפני זה. זה הנקודה שפתאום נפתחו לאנשים העיניים. אל תדאגו, אתם תלמדו בקוונטים מתקדם את הדבר הזה עוד פעם, את הבוזה-איינשטיין condensation.
למה? איך איינשטיין נכנס לשם? הכניס את השם שלך?
הסטטיסטיקה בוזה וזה כי פה אתה לא צריך כלום. כלומר, הקונדנסציה הזאת, בעצם שאתה אומר שיש לי חלקיקים וכולם יכולים לשבת באותה רמה אנרגטית. תחשוב על זה ככה, העיקרון פאולי זה עיקרון באמת קוונטי. עיקרון של בוזה הוא לא עיקרון קוונטי, הוא אתה יכול... כן, הוא סבבה, כן, מה הבעיה שהם ישבו באותה רמה אנרגטית? למה לא? אוקיי? ותשים לב, איינשטיין, אז כל הפיתוחים שלו, האפקט הפוקטואלקטרי וגם האיינשטיינים מוצקים, הוא הלך אחרי פלנק. הוא אמר, בסדר, אז יש לי פה קווינטות של אנרגיות, ונניח שבוא נשים את כולם באותה אנרגיה תחתית, אוקיי? ונסכם על האנרגיות שלהם. וזהו. ואז אתה מקבל את זה. אתה מקבל את הקונדנסציה ברגע שאתה עושה גרנד קנוני, והוא הכיר את הגרנד קנוני, אוקיי? וזה שהחלקיקים יכולים לשבת באותה רמה אנרגטית. זה הכל. כלומר, זה בעצם, הפרמיונים הם באמת תופעה קוונטית כזאת של איסור פאולי. הבוזונים, אתה לא חייב לחשוב על בוזונים ועל משפט שרדינגר ועל כל הדברים האלה. אתה יכול להגיד, יש לי חלקיקים והם גז, אז יש להם כל מיני רמות אנרגטיות, פשוטות, כן? מה אתה צריך?
בעצם התקופות מצבים רק קיבלנו את זה.
כן, כן, בדיוק. לא, שני גורמים. אפסילון וחצי היה שם, והיה את בעצם מופיע לן של 1 מינוס E במינוס בטא אפסילון מינוס מיו. אתה צריך את הגודל הזה. אתה צריך את המיו הזה, בעצם שהיא תופיע לך מאיפה. ואיינשטיין השתמש בדברים האלה כבר לפני זה. האפקט הפוטואלקטרי, הפלנק בנוי על הדברים האלה, רק בלי מיואים קנוני. והפוטואלקטרי של איינשטיין בנוי על דבר כזה. הוא ייסד את הקוונטים בלי לייסד את הקוונטים, אוקיי? למרות שהוא לקח את זה מפלנק, אבל בסדר. והשתמש בזה תוך כדי זה שהוא מתנגד לרעיון של קוונטים כל הזמן. ולא הפריע לו יותר מדי. לא, אני מניח שפרמיונים היו מפריעים לו קצת, כי זה היה מפריע לו לא קצת, אפילו מאוד. הרי הבייבי שלו זה תורת הגרביטציה. בתורת הגרביטציה, ההשפעה יש לה, היא חייבת לעבור במהירות מקסימלית של מהירות האור. אתה לא יכול. עכשיו, ברגע שיש לך פאולי, איסור של פאולי, ההשפעה הזאת מיידי, ככה. אוקיי, אז זה היה מפריע לו, אבל בוזונים, בסדר, לא מפריעים, כמו חלקיקים רגילים. מה, חלקיקים, אז לא משפיעים, כמו גז קלאסי. לא משפיע, מה מפריע לי? אז זה הסיפור של בוזה-איינשטיין, כי זה עניין סטטיסטי, אוקיי? זה פחות עניין קוונטי, אוקיי? זה עניין סטטיסטי בלבד.
הייתה לי עוד שאלה קטנה.
כן.
מה זה הלמדתי הזה? כי קיפלנו כמה קבועים לתוך איזשהו קבוע, נתנו...
סתם כדי לא לסחוב דברים קבועים.
לא, אבל קראנו לו thermal wavelength, זה נשמע כמו משהו ש... משמעות.
כי בסוף, אז תשים לב, מה אנחנו אמרנו? משמעות היסטורית. אנחנו בסוף אמרנו שלדברים האלה, אוקיי, יש להם איזשהו אורך גל. ולמדתי הזה, הרי בסוף דחפנו פנימה גלים, אוקיי? והגלים האלה הם איכשהו מתארים כמה חלקיקים יכולים לשבת לך בפנים. תשים לב, היה שם איזשהו N, G0, V, אוקיי? למדה T בשלישית, אוקיי? ופה יש פה איזשהו פרי פקטור, אבל הוא חסר יחידות, נכון? ופה יש פה איזשהו F, 3 חצאים. הגודל הזה הוא חסר יחידות, הוא פרי פקטור. זה פרי פקטור חסר יחידות. מה זה N? N, אתה אומר, זה הגודל שלי, הנפח, וחלקי כמה תופס כל חלקיק, או נפח פר חלקיק. נכון?
כן.
אם אני לוקח, נניח אין אינטראקציה בין החלקיקים האלה. אז אני לוקח את הנפח הכללי, מחלק לנפח שתופס כל חלקיק, אני מקבל את מספר חלקיקים שיש לי. אוקיי? יש לי V, אז למדה T בשלישית אני אומר להגיד שגודל, בוא נניח שהחלקיק שלי זה איזושהי קופסה עם נקרא לזה LT ו-LT, או סליחה, למדה T. אז מה שעומד לי פה זה נפח פר חלקיק. אז למדה T זה אורך של קופסה כזאת, ולכן זה wavelength. כי זה חלקיקים גלים, ולכן wavelength. אבל זה גודל של חלקיק.
אז זה לא אמור לצאת כאילו, גודל של חלקיק זה לא...
אבל זה לא גודל, אם זה קוונטי, אז זה פחות או יותר מה הגודל של חלקיק.
אז זה מתקשר אבל לאורך גל באמת של החלקיק.
מה זה אורך גל של חלקיק? זה פחות או יותר, כן? איפה החלקיק מרוכז.
נכון.
נכון? זהו. אז אורך גל של חלקיק הוא סוג של מראה לך איפה החלקיק מרוכז, הוא גם מראה לך קלאסית מה הגודל של החלקיק.
זה חלקי 2 פאי שווה לקייק שהתחלנו איתו?
לא. זה אפקטיבי. הנוסחה הזאת היא אפקטיבית. בואי נניח שאני הייתי אומר לך, ינון, יש לי חלקיקים, כן? כל חלקיק יש לו, הוא בגודל של הקופסה הזאת, שהצלע של הקופסה הזאת זה A, אז גודל של חלקיק זה A בשלישית, אוקיי? מה הנפח של כל החלקיקים ביחד? היית אומר לי זה A בשלישית כפול N שווה לנפח, נכון?
כן.
אז N שווה ל-B חלקי A בשלישית, וזה A זה סדר גודל של אורך של חלקיק איפה שהוא חי. אוקיי? אז אותו דבר פה, אני מסתכל על, יש לי פה V, יש לי חלקי איזשהו גודל בשלישית, אז אני אקרא לגודל הזה, האורך גל של החלקיק, שהוא מראה כמה החלקיק מתפרס.
כאילו נניח והחלקיק לא היה מרוח על כל המרחב, אלא היה לוקלייז ל...
בדיוק. זה ניסיון לתיאור קלאסי של דברים קוונטיים.
כן, הבנתי. אחלה.
בהצלחה.
תודה רבה.